It's kind of funny too, because when you go back and listen to it, you can hear all of this stuff you guys say.
Like that one kid talking last year.
Yeah. Let's just start with some easy examples. Rules of exponents. You might be a little rusty at this, but I'm sure it'll come back pretty quick. Or I'm hoping. I'm being optimistic. Ooh. A couple of problems to try. See what you can make out of those. Ooh, that reminds me of something. Pause, I'm pausing. So, -3 quantity squared. What are we thinking?
9? 9 or -9? What do you think? I'll tell you, one of these is -9, the other one's +9. Isn't this thing cool? I love this thing cool. Anyway, this is +9. Okay? And the reason I did this, I know they both look pretty much the same, but you need to realize there's a big difference here. The difference is what's being squared. This is the exponent, correct? What's being squared here? -3 is being squared. Part B is different. Here's the exponent. What's being squared? 3 is being squared. Okay? The negative is not being squared. It's not being raised to the second power. You have to follow your rules of order of operations. You square, and this is really -1. You multiply. So it's 3 squared, which is 9, and then you multiply it by -1. So the answer is -9. Big difference.
Also a very common mistake. Just something to try to remember. What about part C? We add the exponents, yeah. Is it 5 to the power of 6 or 25 to the power of 6? Because those are both two different. Makes you kind of think for a second. God, is it 5 to the 6th power or 25 to the 6th power? Here's something you can think about. 5 squared, isn't that 5 times 5? And then 5 to the 4th is 5 times 5 times 5 times 5. So how many 5s are there? So it's 5 to the 6th. The base doesn't change. Okay? If the bases match, then it stays the same. You add the exponents. Okay, these are some of the properties you hopefully. Did these look familiar at all from last year? You should have gone over most of these. Let's try another one. Example 2. Getting a little more complicated now. Negative exponents. How the crap do we deal with those? Start at part A here.
want you to do. Even if you're not finished with all of them, or if you're stuck on one, I want you to turn to somebody next to you or behind you. Get with somebody around you and discuss, hey, what'd you get for part A? What'd you get for part B? Okay. So tell me your name again. Rachel. Answer's 1. It is. Thank you. Anything, this is something that it's just best to commit to memory. Anything to a power of 0 is always 1. Except there is 1. If it's 0 to the power, that's something else completely. But anything to a power of 0 is equal to 1. Okay? It's just something you want to try to remember. I can show you why. We don't really have time to either. That's not a real hard proof, but just remember, anything to a power of 0 is equal to 1. This one's a bit trickier. As I was walking around, I didn't see many correct answers. But no, just your own. Good. Now tell me your name again. Desire. 1/8. 1 over 8. Okay, this is a little bit hard to remember. It was taught last year, or it was supposed to be taught in algebra 2. But how do you know it was 1/8? How do we deal with negative exponents? That's something else you really want to try to remember. Negative exponents don't make negative numbers; they make fractions. Negative exponents produce fractions.
Okay, I kind of like goofy phrases to help you remember things. Here's one of them. Let me erase this here. 2 to the negative third, you can think about that as a fraction, right? 2 to the negative third over 1. You guys all right with that?
Not that I know of for this class. Unless anybody really... I tried to scare him, but I guess I'm not that scary. No.
So anyway, here's a phrase you can try to remember with negative exponents. Okay? Call this the line. This is the fraction bar, right? Call it the line. If it has a negative exponent, it hops the line and changes the sign. Okay? If you had me last year, I use this phrase all the time. Negative exponent hops the line, changes sign. So really this turns into 1 over 2 to the third. 2 to the positive third. The negative exponent changes to a positive exponent. What's 2 to the third power?
8. So it changes into 1/8.
Okay. All right. Part C, I didn't really...
Does anybody want to come up? I can choose. This is my participation board. I usually write on that one over there. I don't like to write so much on this one. You want to try it, Sam?
Yeah, sure.
Let me help you a little bit. Before you start writing, what was that phrase I just said? Up the line. So these have to move up here, right? Making how many? Oh, now you did it. Still over here. There you go.
This is hard. How do you do this?
Professional teacher. That is the correct answer. X to the 5th power. For the same reason as part B. These have negative exponents. What do you do with negative exponents? Hop the line, change the sign. So you're taking these 3 x's, moving them up here with those 2, making how many x's? There's 5 of them up there. X to the 5th power. Okay?
Moving on. These are going to start to get super fun. Example 3. We got to kind of speed this up too. . Gesundheit. Like that? Does that sound like a German?
Like, one of those rookie Germans, like.
It's racist, and I won't stand for it. Usually I do like to give you time to work these out on your own. We're running down to about 20 minutes there, so still have a few more things to get through. So I'm just going to jump right in. If you have an expression that's being raised to an exponent, the first thing, and this is probably one of my biggest pet peeves in all of basic algebra, not college algebra, but just basic algebra. If all of the terms are multiplying each other, then you distribute the exponent to all the terms. Only if all the terms are multiplying each other. Where you start to run into trouble would be a problem like this. Do you see a difference between these two problems here? Okay, these two terms are adding each other. Okay, you do not just distribute the exponent to those two terms. That doesn't work. Okay, we'll actually learn about that later on in the semester. But in this case, since all the terms are multiplying each other together, you can evaluate the exponent onto all the terms. 3 to the 4th power is 81. Oh boy, what about x squared to the 4th? X to the 8th. If you have a power to a power, you multiply, so that's x to the 8th. Y to the negative 4. And just as a matter of writing this in its fully simplified form, you never leave anything with a negative exponent. It's like not simplifying a fraction. You just don't do it. So fully simplified is 81x to the 8th over, y to the 4th. It has to hop the line, switch to sign to have a positive exponent. Okay, sorry, I know I'm going super quick, but you guys are okay. You can keep up. There's 2 or 3 different ways you could probably do part B. I'll show you the way I would do this one if it were me. Did I?
Yeah.
I don't even know what I'm saying. I do rhyme most of the time. Anyway, here's what I would do first. You notice inside the parenthesis that some of this stuff gets simplified first before you evaluate this exponent. Do you see what I'm talking about? So if it were me, I would simplify inside the parenthesis first and then evaluate this exponent. That's one way you could do it. I'm not saying it's the best way or the right way, it's just how I would do it. The other way you could do it is you could evaluate the exponent to everything in the numerator and the denominator and then simplify. So it's up to you, but here's what I'm going to do. Simplify inside the parenthesis first. 6 divided by 3 is 2, so I'm going to put a 2 on the top there. X to the negative 2 divided by x. That really has a 1 right there. It's x to the 1st power. So this x to the negative 2 hops down here to combine with all of these, making x to the 3rd. Now, what about the y's? We didn't really talk about this yet. It's still something that you might recall from last year. How do we deal with those? None of them are negative, so there's not going to be any hopping of lines and switching signs here. You subtract. If you're dividing, you subtract. 4 minus 1 is 3. And since there's more of them in the denominator, that's where they stay. There's 3 of them in the denominator, so it's y to the 3rd. Now we would evaluate the exponent to all the terms. So you're going to get a 4 in the numerator and an x to the 6, y to the 6. Where did the 6 come from?
you multiply. 3 times 2. If you had a power, raised to a power, you multiply.
All right, that's all the exponent stuff we need. Let's get into radicals. Radical. Here's some basic stuff that you ought to be able to do at this point in a pre-calculus class. Let's start with simplifying radicals. Example 4. Now, I'm not expecting that you remember it 100% like right now today, but it should be something you say, oh yeah, I remember that. I can do this now once you see it. If I asked you to simplify square root of 12, for example. Simplify doesn't mean evaluate. I'm not asking you to type this into a calculator and give me the decimal. I'm asking for something like 3 square roots of 5, or just something that's in simplified form. Do you understand what I'm asking you to do? It's not 3 square roots of 5. That's the wrong answer, but it's something like that. Some of you will draw the little factor tree underneath, and that's okay. If you learned it that way and you use that way, that's great. I'm not saying there's anything wrong with that. It is a little bit longer, especially if you get real big numbers like, I don't know, square root of 214, things like that. You're not going to want to draw a big tiny factor tree. Here's how I teach it. If this were a basic algebra class, what multiplies into 12 that's a perfect square? 4. 4 times 3. Okay. One of the properties of radicals says if you're multiplying 2 terms underneath a radical, you separate it into 2 radicals. Square root of 4 is 2. So this changes into 2 square roots of 3. Okay, that's just a basic skill that at this point you should be able to do. We need to move beyond square roots though into other types of roots, because radical doesn't just mean square roots, cube roots, fourth roots, whatever it is. Let's try cube root. Cube root of 54. Now again, I would like to give you time to work this out. We really don't have the time, so let's just write this down. $54 is 27 times 2. Now 54 is a lot of other things. It's not just 27 times 2, but why in particular am I choosing 27 times 2? 27 is a perfect cube is what it's called. 27 is a perfect cube. So you want to use the highest perfect whatever number you can, in this case a perfect cube. So you change this into the cube root of 27 times the cube root of 2. Cube root of 27. Now cube root, for those who are like, what the crap is a cube root? It's something multiplied with itself 3 times. What times what times what? Same number multiplied 3 times equals 27. 3. So the cube root of 27 is 3. So this is 3 cube roots of 2. Okay? Here are some other skills you're going to need. These ones are the fun ones. All right, I'm sorry about this. I hate to have to do this to you. Remember these kind of problems from Algebra 2 last year? Remember these? Not the easiest of problems. I myself would recommend that you break this up similar to how we split up all of these into separate roots. So this could be the square root of 8 times the square root of x to the 7 times the square root of x to the 6. You can split this up if you want. You don't have to do it this way. actually show you two different ways here real quick. Square root of 8, that changes into 2 root 2. Oh, hold on now, that should be a y. What the heck? There we go, y to the 6. So, exponents inside of a radical. Okay? There was something I need to go over real quick. When you have a radical, this right here is called the index. Okay? So if we're talking about a square root in particular, what would you say the index is? The index is 2. It's just never written. Okay? Right here, this would be an index of 3. So every radical has what's called an index. If you have an expression with an exponent inside of a radical, you divide the exponent by the index. But in this case, 7 doesn't divide by 2, right? So what you were supposed to have learned last year is you need to manipulate this so that you do end up with something that's divisible by 2. You would change this into x to the 6 times x to the 1. 6 is divisible by 2, correct? Now, y to the 6th power, I'm just going to leave that as it is because it's already divisible by 2. Now this, let's talk about this in particular. This is going to end up looking something like this here or something like this here where we have something in front of the radical, something left inside. X to the 6 is the even exponent. That's going to divide by 2. 6 divided by 2 is 3. So this is going to change to an x to the 3rd that moves to the front. And the x to the 1st power stays on the inside. Now, we haven't got there yet. That's just this. Okay. This expression here, the square root of y to the 6, since this is already even, you divide 6 by 2. 6 divided by 2 is y to the 3rd. Now, do we have to have anything left over, like another root there? Is there anything left over there that you can see? There's nothing left over. There's no need for any more radicals. And then we drop this down. We have 2. So this is where we are now. We need to clean this up a little bit. When you're multiplying radicals, anything on the outside multiplies together. Anything on the inside of a radical multiplies together. Good morning. What's your name?
800.
What was it? Did they just add you to the class?
Yeah, I just barely.
Okay. Which class are you coming from?
I was at UCAS last year.
So new to the school. Welcome.
Yeah. Well,
Great.
kind of new. I was here in 9th grade.
Okay. Great school, huh? Talk about Westlake. UCAS, I'm sure is great, but Westlake is cool. Westlake is pretty cool. So anyway, you multiply everything on the outside, you're going to get 2 x to the 3rd, y to the 3rd. You multiply everything on the inside, and get a square root of 2x. I know, not the easiest of problems. These are some things you're going to have to practice on your homework, you guys. Go through your homework, try it. If you run into trouble, ask for help. Okay? That's one thing you need to realize. In these kind of classes in college, you ask the professor for help if you don't understand something. Okay? Or you get together with friends. You don't just sit there not knowing something thinking that it's magically going to start happening. You got to seek out the help. Be willing to go out of your comfort zone and first admit that you need help and then go find the help. Yeah? You just got to go pick it up from the textbook office. Yeah. Let's go on to the very last thing. Rational exponents. We got to breeze through this in about 4 minutes. Here's the property. If you have something of this form, the nth root of x to the power of m you can rewrite that as x to the m over n. Those are called rational exponents. Rational exponents are nothing more than radical expressions. Okay? They're exactly the same thing. So, something like this. Eight to the 2/3. Now, some of you might get to the point where you can just rattle off the answer to this. The answer is 4. Okay. Let's see what. First thing I would suggest is you rewrite this in radical form. The 3 on the bottom tells you what type of root this is going to be. This is a cube root, so I'd write this as the cube root of 8 squared. Now here you have two options. You could either take 8 and square it and then take the cube root, or you can take the cube root of 8 and square it last. Both will give you the same answer. It doesn't matter what order you go in. Usually it's easier to evaluate the root first and then the exponent. So what's the cube root of 8? 2. 2 squared? 4. Okay? That's how those rational exponents work. Okay? They're mainly useful for weird problems like this. If I asked you to evaluate this in radical form like this can seem pretty confusing, right? The square root of x times the square root inside of radical. You ever seen anything like this? It's kind of funky in radical form, okay? That's why you want to use this form, rational exponent. If you ever get into trouble at some point in a problem, try the other form. Go back and forth, because sometimes in the other form it might make more sense. For example, now I want you guys to look at this and compare. Both of these are exactly the same. One's radical form, one's rational exponent form. Okay? Where did the 1/2 come from, by the way? Did I just make up numbers? Am I making up numbers here? Why does it have to be 1/2? It's a square root. There's an index of 2. Okay? Let's combine this here. X times x to the 1/2. That's really x to the first power. What do you do when you're multiplying terms together? We talked about this a couple minutes ago.
You combine the exponents by, you said it, somebody said it over here. You add them. 1 plus 1/2. Close.
1 plus 1/2 is 1.5 or 3/2. So this changes into x to the 3/2.
And now we have that issue. What happens when you have a power to a power, would you say? X to the 3/4. How do you get there? You multiply the powers now.
So this is x to the 3/4. So being able to switch back and forth between rational exponent form and radical form
Can make a potentially impossible problem. This one looks pretty difficult to do. You switch it over to rational exponent form, wasn't that bad. Okay. So,
that's in a nutshell. It was a little bit quicker than I would have liked, but